We're going to start our conversation about climate change with a little bit of history. I'm sure that probably all of you are already aware that climate change is happening, and if you had any questions about whether or not this is caused by people or not, it's useful to just go ahead and take a look at this graph. This is a graph on the NASA website, and it's tracking the carbon dioxide in the atmosphere for the past 800,000 years. And the carbon dioxide levels are tracked through ice core analysis. So you also probably have heard of these kinds of experiments. What they do is they go to an undisturbed ice sheet. Some of them are in Greenland. I don't know how long they're going to last now, since our ice sheets are starting to melt in places. Anyhow, so they drill down as far as they can, and then they keep those cores really super cold, and they look at them under a microscope, and they slice off the layers that are separated by a layer of dirt, because in the non-snowing season, then you get a deposition of dust and things like that. So they can tell where each year ends, and then they take that amount of ice that they collect, and they analyze what isotopes of carbon are present and which isotopes of oxygen are present. And there's a set of analysis that they can do that relates the evaporation rate of the different isotopes of oxygen in water to whatever the temperature was. And so they can track then they can look at how much carbon dioxide got trapped in it. So anyway, point being, as a scientist, you can track how much carbon dioxide is in ancient ice by looking at isotope ratios. You can also get a sense for what the temperature is by looking at oxygen ratios. So you can see by this little white level over here, we're up over 400 parts per million, which we've never seen in any of the ice core data. We had never seen levels above 300 parts per million. So if anybody says to you, oh, well, global climate change is happening, but how do we know it's caused by people? Just look at this part of the graph, and hopefully that will convince anybody who you need to convince. Anyhow, we're not going to talk about the carbon dioxide levels yet. First, we're going to get back into a little bit about how, how the atmosphere warms the Earth. And so we might also need a little bit of information here about how we talk about light and energy. So we've already talked about light and energy in terms of things like how to calculate energy from wavelength. Hold on. That's a little bit too big. Hc over lambda, or h nu. And this is just for photons and specific wavelengths of energy. But what we also talk about is we can talk about energy radiating from things and how much that energy is. So energy radiates from almost everything. We're mostly used to thinking of things like the sun and stars as being things that radiate energy, but they just happen to radiate in the visible, and lots of other things radiate in other wavelengths, and not all of them are visible. So when people were studying radiation not in the visible, they called this blackbody radiation because they were not in the visible, so therefore black, right? And blackbody radiation can be modeled by an equation that Max Planck developed about 100 years ago. And it looks at objects giving off heat as well as light. So it works for the sun as well. Emission in the visible. as well as infrared and microwave and so on and so forth. So the equation that Max Planck came up with was the energy, E, in terms of the wavelength, could be calculated by this kind of complicated equation. This is an H, and I'll define constants in a little bit. Okay, so all of our constants. H is Planck's constant. He did not name it that, but it was named after him. And it's a teeny tiny number. We used it in that energy equation of light already, so hopefully that one's familiar. C is the speed of light. Lambda is the wavelength, and you put it in whatever units you need it to be in to be consistent with the rest of your equation. So probably here it's like in meters, I'm guessing. And then let's see what we have. T is temperature in Kelvin. And then K is the Boltzmann constant. And I have that number here too. That value is 1.3806 times 10 to the minus 23rd joules per mole Kelvin, or sometimes you'll see people write it in some other units, but functionally what this really is just the gas constant divided by Avogadro's number. And so that's where we get the moles in here. Or excuse me, it's not even joules per mole Kelvin, it's just joules per Kelvin. All right, so this is a complicated equation with a lot of constants and everything, and you really don't need to remember this equation at all. But what I want you to get out of this equation is these main points. And so this first one is that the energy emitted is a function of the temperature and the wavelength, but we're mainly going to focus on the temperature dependence here. And the hotter something is, overall, the shorter the wavelengths. And so if something is cooler, it's going to be shifted to longer wavelengths. If it's hotter, it's going to be shifted to shorter wavelengths. And what I mean by shifted here is that the equation, this Planck's equation, is an energy distribution. And the energy distribution looks like this. So you can draw this in terms of the wavelength, which is what we have up above. You will also see some of these equations done in terms of the frequency. And what you'll look at is you will basically get this kind of curve that tails off on the long wavelength side. So this is increasing wavelength and therefore decreasing energy. And depending on what the temperature is, I don't know if these cross, probably. But anyway, if this is T1 and this is T2, then this curve is for the hotter of the two objects. And what you get out of this curve is that hotter objects release more energy, and the maximum wavelength location, we're going to call this Lambda Max, is shifted to shorter wavelengths. So I'm going to write that down, that the hotter we have, then our Lambda Max is shifted left. I better not say left, to shorter wavelengths. And for hotter, you also have more total energy released. And these are both totally logical kinds of results. Okay, so from these two, we can move on to a third big idea, which is that we can predict where lambda max is. So if you are somebody who has done calculus before, you know that we can use calculus to find the location of a maximum or a minimum. And the short version is you take the derivative and you set it equal to 0 because at this particular point we have a 0 slope. So anyway, you can do that. We aren't going to do that right now, but we can calculate it. The equation to predict lambda max is able to be found in various different forms. The short form of this gives us the wavelength in micrometers, and it's 2,900 micrometers divided by the temperature in Kelvin. If you want to see a slightly longer version of this equation, you can find them. You can find HC over 4.965 kBT. So this is the Boltzmann constant again. And then this 4.965 is a numerical solution to part of the derivative that has a funky mathematical function in it. So anyway, that part is unitless. Anyhow, it's perfectly okay for us to go with this easy version of it. I just want you to keep in mind that the temperature units will cancel out because they're sort of glommed into this 2,900 micrometers. And that functionally we just plug in the temperature in Kelvin and then the units will work out fine. So this is sort of like the equation that we saw back in chapter 2, 3, whatever the previous chapter was, and where they'd already kind of calculated a bunch of the numbers out. Anyhow, so what we can do is we can predict the maximum wavelength emission location, which helps us to predict the color of something based on its temperature. So let's take for an example. Let's think about a star. So Sirius, for example, has a lambda max of 72 nanometers. So we can estimate its temperature from that. So we can just rearrange this equation right here and solve for T instead. So 2,900 micrometers divided by lambda max in micrometers. We need to do a little bit of unit conversion here, but that's no problem. So 2,900 micrometers divided by 72 nanometers, and we're going to convert those nanometers. I always have to go through meters. If you don't have to, that's cool. I guess after the end of this, I'll probably remember that it's 1,000 nanometers per micrometer. All right, so if we calculate this out, then we get 40277 Kelvin. So around 40,000 Kelvin in temperature for this star. That's pretty hot. It's quite a bit hotter than our sun. Anyhow, so that's just an example of calculating the temperature from the wavelength, or you could go the other way around as well, and we will in a little bit. That's the third big idea. The next big idea that I want us to know about is that you can also calculate the total energy and the total energy for a equation, or for a function like this, anytime we want to calculate the total anything, we would just take the integral if we were doing calculus. So we aren't going to do the integral. The integral just sums up the entire area. And the equation that you get if you do that integral is you get 2 pi to the 5th, k, that's k Boltzmann, 4th. Maybe I'll put a b there, just so we can really keep it straight. So it's not a rate constant, it's the Boltzmann constant. T to the 4th, that's temperature, over 15, the number, c squared, that's the speed of light, and the Planck's constant cubed. So since most of these guys are constants, Boltzmann constant, c squared, h cubed, and then these other numbers are just constants, you can actually just group them all together into one unit called alpha, which is approximately 5.67 times 10 to the minus 8 watt per meter squared Kelvin to the 4th. And this is called the Stefan Boltzmann constant. And it's a good idea right now to take a second, pause the video, and actually go through this calculation. Plug in the Boltzmann constant, plug in the speed of light, plug in Planck's constant, and verify that the Stefan Boltzmann constant does actually work out, and these units work out. And one of the pieces of information that you will need in order to do that calculation is to know that a watt is 1 joule over second. So pause the video and take a look and try it out. Okay, hopefully you had a time to go ahead and try that calculation out. It does work out. I tried it myself. So let's practice with some sample calculations that use the equations that we just did. So let's look at the sun, because our system is really the one we're interested in, right? The sun has a temperature of about 6,000 degrees Kelvin. That's a lot cooler than Sirius. So let's take a moment and let's calculate the lambda max and the total energy. So I'm going to write these out, but I'd like you to pause the video before I do and calculate them yourself, and then you can just check them with me in a moment. Okay, here goes. (2900) over T, which is 6,000 Kelvin. I'm pretty sure that the sun emits in the visible range, so I'm going to go ahead and convert from micrometers into nanometers. Indeed, you get about 480 nanometers. That doesn't mean that it doesn't emit in any of the other wavelengths. It just means that that's where it emits the sort of the maximum amount. But it also emits in all of the other visible range and into the UV a little bit, and then quite a bit of IR and radio waves and so on. In fact, we've already looked at the solar spectrum before, and we'll look at it again in a little bit. So the total energy, I'm going to take the Stefan Boltzmann constant, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4th, times 5778 Kelvin to the 4th. And I get 7.35 times 10 to the 7 watt per meter squared. So this amount of energy that's being emitted by the sun, this would be the amount of energy coming off right at the surface. So, and in all directions. But it's in a per meter, so we're talking about like a little surface area on the sun. And so for each one of these meter squared units on the sun, we're getting 7.35 times 10 to the 7 watts, which was joules per second. So this is a rate of energy being produced. Right? I'm just going to write that down again. Watts per meter squared is joules per second per meter squared. And we know that joules is an energy unit, and then per second, so this is like a speed of energy being released per meter squared of surface area. How much energy is being emitted by the sun for each meter squared? So this is quite a bit of energy. So let's compare this now to the Earth. Well, we can Google what the average temperature of the Earth is, and its average temperature is about 288 Kelvin. So we can use this information to calculate what wavelength is being emitted by the Earth. Just doing the opposite of the equation that we just did. 2,900 micrometers divided by 288. We get about 10.1 micrometers. This is in the infrared. And that makes sense, right? The Earth doesn't glow in the visible spectrum. It's not like a sun and gives off visible light. It reflects light from the sun, which is why you can see it from the moon, but it does not glow on its own in the visible range. But if you took one of those, night vision goggles or something, right, you could see the heat radiating off of the Earth compared to the black of outer space if you were on the moon looking at the Earth, or somewhere, that's not right on the Earth's surface, because we wouldn't be able to tell. So that's in the infrared. And we can also calculate our total energy, because we give off energy too. And most things do, unless they're black holes. Watt per meter squared, Kelvin to the fourth, 288 Kelvin to the fourth. So you get 3.9 times 10 squared watts over meters squared. So if you look at this number, the energy being released by the Earth is a lot smaller than this number. And that makes sense. We are not a sun. So these numbers, I don't know, they're so big, I'm not sure we can really make sense of them yet, but we'll try as we go to get a little more comfortable with them. So what we just did was we took the actual Earth's temperature and calculated, where we would be emitting and what the total energy is. But we can actually calculate the predicted temperature. You may or may not have seen some of these calculations before, where people talk about what the temperature of the Earth would be like if we didn't have an atmosphere, if we didn't have the greenhouse effect helping us. And you can calculate this by looking at the incoming energy from the sun and the outgoing energy from the Earth. So if we think about the incoming energy of the sun, let's get an orange ink color here. All right, so here's the sun, not to scale, right? The sun, it's taking me a lot of willpower not to go into that They Might Be Giants song. You can look it up later. So 6.48 times 10 to the 5 kilometers is the radius of the sun. And so when we talk about the energy that it's giving off, it's giving it off from that particular radius. So those little 1 meter squared units, right? So the Earth is a lot further away than that. And of course, this is not going to be to scale, but let's just say that here's our little blue-green dot of the Earth. And this distance is 1.50 times 10 to the 8 kilometers. Which, you know, honestly, given how big the radius of the sun is, this doesn't seem like that far away, right? 10 to the 8th versus 10 to the 5th. I know their powers are their orders of magnitude, but still, it feels like this number is really large. The sun is pretty huge. So we talked about the energy coming from the sun, and it's radiating toward us and also toward, you know, everywhere else because it's radiating in all directions equally. And so only a little bit of it is going to impact us. And the relationship for that is an inverse squared relationship. I should actually put r squared instead of d squared since that's what we're using. All right, so this is a 1 over r squared relationship, that the distance between these two, 1 over that squared decreases the intensity. So whatever this ratio is going to be the factor by how much this energy gets decreased. So let's go ahead and try that out. I'm going to just write it out in words. The ratio of the radii will tell us by what factor the energy decreases. So 1.5 times 10 to the 8th divided by 6.48 times 10 to the 5th kilometers is a factor of 53,600. Okay, so this is the factor of that ratio. Except I forgot to put the squared in here. Okay, now that works a lot better than it did before. All right, so the total energy from the sun was 7.35 times 10 to the 7th watts per meter squared, divided by r squared, divided by 53,600, will get us 1372 watts per meter squared. And this is something called the solar constant. And we use another Greek letter. This is the Greek letter capital omega for the solar constant. So the solar constant helps us understand what fraction of the total energy, which is to say not a whole lot, right? We've divided it by 53,600. So 1/53,600th comes and is impacting on the Earth. However, if we think about how the Earth is a sphere, but the energy that's coming is really only going to hit a particular disk. Ugh, this is a really bad drawing. Let me fix it. So I turned that disk on end. So this is all going to target at a little disk. All right, so a sphere versus a disk or a circle. And the area, the surface area of a sphere is 4 pi r squared. The surface area of the disk is pi r squared. So we really can take our surface area of the sphere divided by the disk, and this is a factor of 4 different between those two areas. So we are actually not going to be getting the whole solar constant hitting the Earth at any one time. We are only going to be getting 1/4 of it. We're going to be getting 1 disk's worth as the sun shines on sort of one face of the planet at a time. So we are reducing this solar radiation a little bit at a time, right? Here was our first reduction. And this was our second reduction. And now we're actually going to have a third reduction. And the third reduction is for something called albedo. And we sometimes use a lowercase a for albedo. And the albedo is how much of the sun's radiation gets reflected, just reflected straight out into space. And this is usually listed as a percentage. And for Earth, our average albedo is about 30%. And the sunlight is getting reflected off of clouds. It could get reflected off of dust. It could get reflected off of snow. So anything that is bright and is going to reflect a lot of the sunlight contributes to the albedo. So that means that the energy actually hitting the Earth from the sun is the solar constant divided by 4 and multiplied by the fraction of the albedo that's left. So 0.7, right? And this is going to be equal then to how much warming we actually get. So we can solve for T to find Earth's predicted temperature. So I just threw a whole bunch of numbers at you. So pause the video and go back and see if you can find all of these constants to fill in so that you can solve for the temperature of the Earth. I'm going to write it out, but I'm going to give you a minute, or I encourage you to take a minute to calculate this. All right, I'm just going to start on the left-hand side. The 1372 for that solar constant, watts per meter squared. 1 minus 0.3 would give me 0.7 for the albedo, divided by 4. This would equal 240.1 watts per meter squared. And this is equal to the Boltzmann constant, 5.67 times 10 to the minus 8 watts per meters squared times T to the 4th. So if I solve for T to the 4th, then I'm going to get 4.23 times 10 to the 9th. And then when I take that 1/4 root, I get 255 Kelvin, which is pretty cold, and this is not what we observe. And the reason why we don't observe this as the actual temperature of the Earth is, of course, because of the greenhouse effect, and so that's what we are going to explore next. So let's take a little break and move on to the next video and learn some more about the greenhouse effect.